Good afternoon, class. Let's get started. If I'm doing my math right, I think we only have 4 classes left. I know that's sad. I enjoy how things work. I enjoy I think, yeah, 4 more days of physics and how things work and fun demos. So what that means is starting like today-ish, we're going to have to start wrapping things up. I do want to have a day or two to do some review, maybe some closing remarks kind of thing. So I want to have a day or two for questions and review and getting ready for the final. Speaking of which, I've gotten some emails. Yes, we have a final. It's on Friday the 13th. Sorry about that. It's 60 multiple choice questions. It is cumulative. No? As opposed to what? It's called a final exam. Isn't that how all? That should not be surprising. I'm sorry if I just blew your mind that final exams are. Did I just hear a boo? Yes, question. 60. 4 times 15. Okay, question. Yeah, great. I'm glad you asked that. So, it's cumulative. That's what a final exam is. I want to see your total understanding all represented in one 3-hour assessment. Good question. Practice. So I will be putting on in Colab. I'll be putting up the 2 midterms and the answers to the 2 midterms. So you can come see me tomorrow during office hours if you want to see your specific midterm and what you wrote down. Did I put B for that one? But if you just want to see the exams and the answers, I'll be putting those on Colab. Also, probably your best practice will be looking over the homeworks. There'll be one more homework actually due Friday. You might have noticed it wasn't due last Friday. It'll be due this Friday. I'm going to assign it today. It's just about electricity, basically. Yes. Exam is what, 9 to noon? And I've gotten like 40 emails about this, especially for, I think most of the athletes have sorted themselves out by now, but if you Google UVA final exam policy in big bold red letters, it says you can't postpone, or you cannot take it early. You cannot take it early. And so it puts us in a tight spot. You're not allowed to take it early, but we're like one of the last exam periods. So just take it on Friday the 13th, 9 to noon if you can. If not, you have to like fill out a form and the dean gets involved. It's a little nutty. Okay, yeah. Curve. Good question. The question is, will there be a curve? Yes, only because a sample size this large always ends up looking like a curve. So the data will look curved whether I do anything to it or not. What I usually do is then take, I'm not trying to be, I'll just explain the process. So the data will be curved usually. And then what I usually do is I just take the data and apply a little algorithm that squishes the data if necessary. So if the mean doesn't fall where I like it, I usually squish the mean over. I've done that to the 2 midterms. I'll do that to the final. So yeah, I don't know where I'll squish it to, but I usually squish the mean over. So I don't know if you can get from my hand gesture when I'm imagining a bell curve, and then I'm imagining pinning one side of the bell curve and then squishing the other side. So the person that gets 100 stays 100, but the person that got a 60 kind of gets pushed over. That's what I'll do. Yeah. Okay. Any other questions about logistics? Yes. Good question. For iClicker participation? Yeah, so your grades, I think there's like 13 weeks or something. Your grades for your iClicker participation are weekly. And so most weeks you either have a 0, 33, 67, or 100 for your grade. And then right now, Colab's dropping 3 of those, I think. So you could skip 9 days, I guess, as long as they were within 3 weeks, and you'd still have 100. So right now it's just dropping 3 weeks. Yes, but That's what's going on in collabs. Because the grades aren't broken out by day. Cool? Okay. Yes. Is a 0. Yeah, I guess we are in that part of the year where we're talking logistics and stuff. That is that's one that's come up several times for several people. If you look on Colab, and by the way, your grades are in Colab. There shouldn't be any surprises. Like, you should go in Colab, see how you're doing. I've gotten emails just recently that says, "Oh wow, I guess according to Colab, I've never been to class, but I see you here every day." If your grade is inaccurate, chances are your iClicker is having a problem. You registered it under a different email or something. There's ways, problems that can arise like that. So all you have to do is just shoot me an email and say, "On my honor, I was in class those days, so give me credit," and I'll change it. It's a nice thing about UVA. I get to take your word for it. Okay. Any other questions? Great. Let's talk about physics. Let's see here. Yeah, so let's get back to the bicycle. I'm going to need a volunteer again to ride the bicycle. Sweet. Oh, wait, yes. Come on down. Excellent. So last time it was Billy. So we're going to pit the rowing team versus track and field. Last time it was Billy. I forget your name, but I do know you run 400 and 800, right? Yep. All right. So, so we're gonna see who can write. I guess it'll be qualitative. Who can light up the light bulb the fastest? So hop on the bike, and as I explained last class, what we're doing. What was your name? What was your name again? Huh? Logan. I knew that. Okay. What we're doing here again is representing a lot of how the power company, basically how the power company makes electricity. We have power here coming we have voltage at our sockets. The reason that is so, unless it's solar powered, somewhere someone is spinning a turbine. So we use hydroelectric, we use coal, we use nuclear power. It's all about spinning a turbine. So now we're going to rely on, and this is a fine way to do it, by the way. Rely on Logan to do your power your cell phone or whatever you're doing. So go ahead and start spinning the pedals. And you'll notice, I believe, it's fairly easy right now, right? Not too tough. But no light bulb. I've disconnected it. Are we on camera? We're not even on camera. Let's see. I don't know if I can fix that right now. Okay, so actually, here, hop off real quick. This is not rocket science. There. We're on camera. Okay, hop back on, please. Okay. So here's what I'm relying on. What I'm relying on Logan to do is just like the power company does. He is spinning a turbine, but so far no light because I have it unplugged. Now hopefully you'll be able to see his legs slow down. I gotcha. Okay. So yeah, now you can see the light bulb is lighting, and it's significantly harder. So I think that's a pretty good demonstration that he's actually having to do work. I'm seeing Logan's breakfast right there. That's what's going on, or lunch maybe, but that's what's lunch. Yeah. So that's what I'm seeing right there. He's actually having to metabolize it. Okay, I think that's, yeah. Go ahead, start pedaling again. I'm gonna unplug it on you. So it's hard. Your legs are having to do work, and now they're not. And you can freewheel. Okay, then it's hard again. Okay, thank you very much. Awesome, appreciate it. So I don't know if I was a tie between the track team and the rowing team, but Billy was asking, I think, what his coach or something about wattage, and like some crazy Olympians can put out 1,500 watts. So imagine a 100-watt light bulb that you're familiar with. A good athlete like Logan or Billy could maybe power 1,500-watt light bulbs. Sure. Probably not all day, probably not for a whole 50-minute class period, but that would be fun. Just have you in the corner seeing how long you can go till it. But no. So just so you can get an idea of how much power the power company is generating, when you powering 1,500-watt light bulbs is like the max output of an Olympian. And I mean, obviously, this building, we're doing that all day long. So it's a whole lot of power. And another thing I did want you to see is that, so Logan can metabolize his breakfast, create mechanical work, and get the bicycle going. And if this was just a normal bicycle, he'd be cruising around. Then when I need to light a light bulb, I'm then just, all I was doing is connecting the electrical circuit. I didn't like put a brake on or anything, but effectively I did. Effectively I engaged an electromechanical brake because all of a sudden the turbine that he was turning was spinning past an open circuit, just some wires sitting there. And that was no problem for him. He just was able to pedal the bike and the wheels turn, and that's about it, not a whole lot of resistance. Then when I engage the circuit, when I close the circuit, all of a sudden there is a complete circuit for him to start driving the magnet past. So he's either turning a coil past a magnet or a magnet past a coil. It's the same thing. Now all of a sudden he is the source of, he is the electromotive force. He is the source of EMF that is driving the circuit. And he is physically moving electrons around a circuit. That takes work. And you saw that as soon as I plugged it in, it was a lot harder for him to pedal because now I'm actually, like I said, it's kind of like a brake. I'm taking some of his energy out, and I'm using his energy to convert that into heat and light on this nice incandescent light bulb. Okay. That was where we left off last class. Any questions? Okay. We only have like one or two more things today. Then we're going to switch gears and start talking about a couple new topics and maybe even get to some review. Probably not. Okay. So this is the picture that we've seen a couple times already. So here, this is the reality that we've come to know over the last couple classes, that in order to generate power, the power company spins something. When you generate power that way, just as a product of the fact that it's going in a circle, you get sinusoidal varying AC voltage. That's, for the most part, a good thing. Like I've said before, the downside is 120 times a second your power goes out. There are maybe things in your house that don't want the power going out 120 times a second, and you have to come up with a different system. But the main benefit of having this nice varying voltage is that I can use transformers. Transformers are pretty much what make all power distribution and all power usage possible. So the power company steps up the power distribution to a crazy high voltage. And we talked about the main advantage of that is at very high voltage you have less current and power, and you don't lose as much power during the distribution. So when I send my electricity across these tall power lines that go across the entire state, if I can jack them up to 500,000 volts, I'm going to have less current, less power losses. So, but a transformer is what makes that possible. Then once you get near my neighborhood, you step it down to maybe 15,000 volts using a step-down transformer. Again, just two coils of wire, totally isolated from each other, except for a common metallic core that enables the changing magnetic field from one to be experienced by the other. But electrically, they're isolated. That's the amazing thing about transformers. Electrically, they're isolated. It's just the magnetic field that's going from one to the other. Step that down to 15,000 volts for the transmission around my neighborhood. And then, let's see the picture that I had before. There it is. Then once I get to my house, I'm going to step it down to the safe voltage that we see at the wall. When you plug something in your house, you're plugging it in to 120 volts. That 120 volts has been stepped down using a transformer. That's those barrels attached to the pole. And now I have 120 volts AC at my plug. So my toaster that's plugged in is seeing up and down voltage. There's a lot of devices like toasters and light bulbs that's totally fine. I can just have the electrons go this way, then this way, then this way, then this way all day long, no problem. When I'm plugging in a light bulb, if the current's going this way and then 120th of a second later it's going that way, my light bulb doesn't care, I still get light. Anything you've ever plugged in that has a battery in it, like most things these days, you're going to want to not only just step that down. So when I plug my phone in, for example, when I plug my phone into the wall to charge it, my phone doesn't need 120 volts, but it also needs DC current. And so all these bricks that you've ever plugged any electrical device into, what does that mean? Oops. Okay. Any electrical device that you've ever plugged into the wall, first of all, has a brick attached to it. That is a transformer. It's just two sets of coils stepping down the voltage. But almost always, they're not only transforming the voltage, they're also rectifying the voltage. And in other words, they're finally turning it into DC. So if you want to charge a battery, and you plugged, most of our stuff nowadays has rechargeable batteries. If you plug a rechargeable battery into AC voltage, so you've got your positive terminal and negative terminal of your battery, and you switch to that 120 times a second, your battery's never going to charge. So we need to take this sine wave and fix it a little bit. And so here's how we do that. Here's an iPhone charger, pretty not legible, but if you, any one of these bricks, I want everyone to try this, any one of these bricks you ever have found around your house plugged into your laptop or your printer or your iPhone, on the device itself, on that little brick, you'll notice it'll say input, and it'll say input, and in this case, if you can read it, 100 to 240 volts, and then a little squiggle. So it says 100 to 240 squiggle. Squiggle means AC. So the input that it's expecting, it does this. And by the way, here's your travel tip for the day. 100 to 240, that encompasses just about the whole planet. So when you go to, when you take your US device and you're traveling to another country that is not on 120, they're on 240, almost all your devices these days, if you look, it'll actually take 240. You don't need that expensive power adapter at the airport. You get to the airport, oh no, I forgot my power adapter, and you go buy they're really expensive to step down the voltage, and they get hot. They're usually a waste. You usually don't need that. All you need really is just a plug adapter. And in a pinch in the hotel, a coat hanger works. So all you need to do is just plug 2 coat hangers in, and you can power whatever your device you, yeah, seriously. Just be safe. Don't plug them in with 2 hands like that. Yes. Yes. Why did, yeah, I wanted to charge my phone in Prague, so I took apart their coffee maker, and I took their plug out and plugged it into my phone. But then, anyway, I put it back together. It worked afterwards. But this is good to know that you don't need to transform the voltage. You just need to adapt the plug. And so if it says 120 to 240, you're fine. The other thing to notice, it says output 5 volts. So we know there's a transformer inside there. Apple has managed to cram 2 windings and a common metallic core into this tiny little white brick. They're amazing how small they are. And notice it says output, and there's that little straight line and 3 lines underneath. That means DC. So the voltage has not only been transformed, but it's been rectified, and it says 1 amp output. And so your phone will charge. Your phone is getting 5 volts and it max out at 1 amp. Caution used for, yeah, question. Julia has to explain the coat hanger thing. This is one of those don't try this at home things, but yeah, so you're in Europe and they've got the funny plug and yours doesn't plug in. If you were to use just one hand and you're going to make sure you're not grounded, you could, don't do this. You could just shove a coat hanger right into the wall. Because I've told you before that being in high voltage is just like being on top of a building. It's only unsafe if you take advantage of the voltage difference. And so as long as your other hand is not touching ground and you're not in a puddle that's also grounded or something, you can take one coat hanger, jam it in one wall, then don't touch that one, take the other coat hanger, jam it into the other hole. Now those 2 coat hangers are 240 volts apart, and then you can just take your plug, you know, maybe like a little hook or something, and just take your plug and wrap it around. Maybe do that first. Like take the coat hanger, wrap it around one plug, the other plug, then plug one in, plug the other in. And you just need those 2 to be 240 volts apart. The plug is just metal. It's just a conductive path. Do whatever you want. Yeah. Or wire. Yeah. Just bare some of the wire from the lamp and then attach it. And just put it back together. I don't know. Yeah. Physics is, that's why you need to know physics. It'll get you out of a pinch in a hotel. Yeah. Oh, good point. So what, yeah, just on the other side of the plug. Yeah, Matt has a good question. What's going on in there? Inside, it's very simple. It's 2 pieces of metal, like a little sandwich, and the plug, the prong part, just slips in there and it makes electrical contact. That part's easy. So your phone is expecting 120 to 240 volts between these 2, and so there's just an electrical contact. And by the way, I only mentioned this just very briefly the other day. I don't know, in the last 50 years or so, we also get a 3rd plug. And so in most plugs nowadays, now the Apple one doesn't care, but most plugs nowadays, there's a 3rd one. And just so you know, that's just an emergency route to ground. So if something goes wrong in your device and it needs to dump current, it's grounded, and that third prong, you could, if you ever got to your junction box outside your house, this is such a tangent, but this is good to know. If you look at the junction box, there's usually a fat, bare copper cable going into a spike in the ground. And that's and if you ever wire a circuit to your house, they'll have the hot and the neutral, and then a big fat neutral cable that goes into a big spike in the ground. That's that third plug. Almost never used. So on a good day, you plug in all your devices in your house, you're just using those two. That's just a safety. If the thing gets shorted, there's a route to ground that's just but they're almost never used. Yeah. Wow. Why is there always a little hole? You totally stumped me. I'm going to go with, that's a good one. I don't know. I'm wondering if some devices, I don't know. I'm not even going to guess. That's a good one. I'm going to Google that later. Or someone's going to tell us in a minute. Billy, did you have a question? Yeah. Yeah. Billy was asking, why did my hand hurt when I plugged myself into the wall? Yeah. Yeah, afterwards you felt like your muscles work on electrical conduction, and you just felt 120 volts in your arm. And so, again, the voltage current wants to go from one side to the other. The fastest route is not just the shortest route. The fastest route is through a lot of this conductive material in this vicinity. And so your arm, depending on how much voltage and how much current, your whole arm will feel tingly and weird for a little while. Yeah. Yeah. Oh, good. That was going to be my guess. My guess was going to be a bump. So when you put it in, the bump kind of grabs it. Nice. Thank you for looking that up. Okay. So just to review, just about everything you've ever plugged in has this. You can read it. You can read what's the input. Again, squiggle line means AC. 100 to 240. That means I can use it in Europe. I don't need an adapter. 50 to 60 hertz. We've already talked about that. So in the U.S., our voltage goes up and down 60 times a second. In Europe, it's 50 times a second. This one will work both. And then the output is 5 volts DC. 5 volts DC. So real quick, how do we do that? We've talked a little bit about diodes before. This is a 4-diode rectifier circuit. Here's what you need to know about that. We've looked at LEDs, light emitting diodes, before. A diode is just an electrical component that allows current to go in one direction. That's it. So a diode just allows electrical current to go in one direction. I can make a nice little 4-diode device right there. And what that does, very clever device. You notice in my two pictures, I go plus on the left. On the left, I've got red, blue. We'll call red positive and blue negative. On the top, I've got my polarity with red on the top, blue on the bottom, and then down below they're flipped. But notice what comes out the other side. The red is on the top either way. And so you can see the path that the current is allowed to make. The path that the current is allowed to make, in either case, I get rectified current. I get voltage always, the top piece is always positive. Here's a slightly different picture. And so you can see my input voltage is AC. It's going up and down, up and down, and up and down. My output voltage, my load, sees the absolute value of a sine wave. So if you took a sine wave and just flipped it all above positive, you'd get this nice bump. So far, for a lot of devices, that's actually enough. That's actually enough. I took apart a hairdryer a while ago, and inside the hairdryer, next to the motor, you just saw 4 diodes. That's all you saw. 4 diodes wired together in a little diamond shape. That was it. Because the motor of that hairdryer, all it needed was just kind of rectified. And by kind of rectified, just nothing going below 0. So otherwise, the motor inside the hairdryer would turn this way, then this way, then this one, this way, and it would just jiggle 120 times a second. That wouldn't work. As long as it's just kind of going the same way, if it's bumpy, it didn't matter. Now, my phone doesn't love bumpy voltage. And so usually what we do is throw in a capacitor. That's that little thing on the right there. You can throw in a capacitor, and actually, if you take apart your Apple charger, there's a couple other devices in there. But for the most part, a capacitor will do it. And what a capacitor does is just fills in the bumps. And a capacitor, we've only talked about super briefly, is just an electrical device that holds charge. And so when the voltage is on its way up, my capacitor is charging. And when my voltage is on the way down, the capacitor discharges into the load and fills in the gaps. And so every time the voltage is diving, my capacitor starts discharging, and I can kind of fill in the gaps. And so just four diodes and a capacitor, and I have a nice rectified DC output. Now, you'll notice it's never totally constant, but we can get it close enough that my devices don't care. Okay. Any questions so far? Cool. Let's do one quick demo / iClicker, and then we'll talk about a couple other things. Okay. iClicker question of the day. I'm going to drop a magnet through a copper tube. I'm going to drop a magnet through a copper tube. What will happen? It will fall normally. Copper is not magnetic. It will fall faster than normal, which is B. It'll fall slower than normal due to induced current. Or D, it'll stick to the inside of the tube because it's a magnet. Take 40 more seconds. Let's see. Oh. Yeah, I've got. No, you might have to email me. Yeah, that is working. Okay. 8 more seconds. Okay, let's give it a shot. So, first of all, let's look at what normal. What do I mean by normal? So, oh, by the way, right now what you're looking at is the view from this camera. Hello, you're looking at the view from that camera, and down at the bottom, I've got a little aluminum tray. So that's what they're going to fall into. So if I take, here's a normal. So here's just a piece of metal. This is not a magnet. This is just a normal piece of metal. Right? Did we see? Let me try that again. I wasn't even looking. Yeah, so you can kind of see it go through that. That would be a normal rate, about accelerating at 9.8, a little bit of contact with the side, so not totally. So now I want to know what's going to happen when I drop a magnet. Here's a nice neodymium magnet. Let's find out. Let's find out and see if we can figure out what happens and why it happens. So here's. Yeah, trippy. It's still going. There it is. Okay. So, let's see, on camera. Yeah, there it is. There's just a normal, there's my magnet. The focus. Okay. So you can see the. You're going to focus it on the way down. Oh, you focus it on the way you follow it. There it is. That's nice. Nice. That's nice. There it is. Oh, that's much better. Al. Thank you. That was smart. Now let's try that again. Okay, so now that's out of focus. What if I see it again? There it is. I'm down here. Wait, there I am. Okay, so I've got a neodymium magnet when you drop it through. That is pretty trippy. So notice there's a lot of space between the tube and the magnet. So it's not like it's stuck. If I were to try to put a piece of Play-Doh or something through there, it might take forever to fall through. But it's falling at a very low rate compared to that other just piece of metal I had up here a second ago. There it is. That as opposed to that. And let's try one more magnet. This one's a little bit bigger, and so we'll talk about what's going on in here, what a different effect there might be for this larger one. This one might be a while. Yep. That's impressive. There it goes. Okay. So so the answer is what? C. All right. Nice job. Nice work. 108 people. Okay. So I think it sounds like a lot. I mean, we've talked about this already. So just as a quick review, what the heck is going on here? We have just a conductive tube. There's nothing magnetic about that tube. Oh, and by the way, if I take my magnets here, so it's not like it was sticking. So there's iron right there. It's not like it was sticking to the copper tube on the way down. But what we have here is the copper tube is metallic. It does have lots of mobile electrons. Copper is a great conductor. So on the way down, the copper material sees this incoming magnetic field. And so the main point of what we've been talking about the last few days is that I can induce current. That's what Logan was doing up here. I can induce current by a changing magnetic field. And so here's some copper atoms just minding their own business, and here comes an incoming magnetic field. And so I don't know, maybe it's south. Here comes a south magnetic field on the way down. Those copper atoms are that'll induce a current because it's changing, because it's incoming. That'll induce a current in the copper. The copper will create a current that'll induce a current in the copper that will oppose the incoming south. So here comes a south magnetic field. That will create a tiny electromagnet in the copper itself that'll create a south to oppose it. And those opposing forces will, they'll oppose each other. And that'll create a force on the magnet. Now, you saw the magnet tumbled, but electrons are very mobile. They're very light. And so the current is constantly changing to oppose whatever configuration is coming down. So even as it tumbles, so I've sort of created a south because of the incoming south. And then all of a sudden the magnet tumbles, and then I'll create a north, and it'll happen very rapidly. And that'll happen all the way down. And that'll slow it down. That's a good example of an induced magnetic field. Okay. I had 9 minutes left. I kind of want to use some of my other toys up here. So what we're going to do is we're going to skip over a couple things we'll talk about next class. To get to, here's where I really want to get to. This will kind of lead us to the end of the year. And where I wanted to get to today is so many of the things we've been talking about this semester, whether it's momentum and energy and projectiles, or whether it's electricity and magnetism, can be thought of, are often lumped into something called classical physics. And so the insights that Newton gave us starting in the 1600s, that's often lumped in as Newtonian physics or classical physics. And there's some crazy things we've learned in the last century that don't negate all of our understandings of classical physics, but give us a much weirder view of the universe. And so when you guys leave here after just 4 more class periods, I want you to not only know how things work, which is a pretty nice thing to know, and understand some of the macro understandings of why things behave the way they do, but also some of the weird things we've learned in the last 100 years that have to do with classical physics and have to do with quantum mechanics. And so one of my favorite examples of modern physics and quantum physics is the idea of superconductivity. Superconductivity is something that we discovered around 100 years ago, had no idea why it was. And so here's a good picture of superconductivity. What you're looking at up there is we've already seen that the conductivity of the conductivity of something goes up, or the resistivity goes down when you cool it down. So the other day when I was shooting rings off of that magnet, I cooled one of the aluminum rings down, and because it was colder, it had less resistance. And that is understandable from a classical standpoint. That if electricity is just electrons flowing through a lattice of positive ions, then the more bumping that happens, that's called resistance. So if I cool the material down, there's less atomic jiggling, and the electrons have an easier time getting through. But until you get to absolute zero, there's always going to be jiggling. There's always going to be an electromagnetic interaction between these electrons as they try to flow through and the positive ions that they're trying to get through. So from a classical perspective, there's always going to be resistance, and that makes sense. Then you cool stuff down, it'll be better. Now, what happens when we get to superconductivity that was discovered, literally, and you can see from that graph, you're cooling something down, and then boom, resistance just hits zero. Rarely in physics do you get zero. You often get like asymptotically approaching zero. Zero at infinity or something like that. Rarely just you see something go boom, 0.0. Okay, let's measure that a little more accurately. 0.0000. And there's no 1 at the end of that. It just drops to 0. And so the only way we can explain that is through quantum physics, through our understanding that, and we'll talk more about this next class, that what was going on in like the 1920s, where we were starting to realize, wow, some of our classical understandings of the universe are actually, there's some weird stuff going on down at the subatomic level, and we'll talk a little more about that next class. So, and superconductivity is one of those things. And again, I'll explain this a little more next class because we only have a few minutes left. But you get matter, the stuff that you and I are very familiar with, you, me, tables, chairs, that stuff is stuff because of some very rigid rules of physics. And so the reason you are not condensing into a zero thickness puddle on the floor right now is the beauty of the way, like it's very rigid rules. And so you can rest assured that you're not going to do that. But all of a sudden we get these materials that basically do that basically just throw all the rules of physics out the window and start adhering to and behaving according to totally different rules. And it's wild to see. And so superconductivity is one of those things. So what I have up here is I have a piece of superconductor, and what that means is when I cool it to its, when I cool it below its critical temperature, Tc right there, so I've got a piece of superconductor here. When I cool it below its critical temperature, its resistance will literally go to 0. And it's just a piece of metal, but what's cool about it is once I induce current in it, like I did here, once I induce current in it, that current is there to stay. It is zero resistance. That current will flow without resistance and will go forever. In fact, here in the physics building, we have magnets that you can just turn on, get the current going, and then turn them off. And the currents just keep going. So you have an electromagnet that doesn't need any voltage. You can turn it off, go home for the night, come back the next day, and the electrons are still whizzing around because there's 0.0 resistance. So I might get to half of this demonstration today, and we'll have to finish it up next class. So here's my liquid nitrogen, which we've already played with before. It's very cold. I think it's 77 Kelvin. That's pretty chilly. And the reason I would like to play with this today is because I need to cool my superconductor down to below its critical temperature. And so let's see, on camera you can see it. So here's my superconductor right here. There it is. There's my superconductor. And this is just a very thin film of superconducting material. I'm going to place inside a little pad here. And the reason I'm going to place inside that pad is just going to hold on to the liquid nitrogen for me. And so I'm going to drop that guy in there. Probably shouldn't do that with my fingers. There. And as we talked about a couple classes ago, I can see the boiling, and that's a liquid nitrogen turning back into a gas, so it's liquid. It's turning back into a gas as it absorbs thermal energy from the superconductor, which was at room temperature a second ago. Now it's cooling down, and I know it's cold when it stops boiling, and so it's roughly at about 77 degrees Kelvin, which the important point for me is it's low enough, it's cold enough, so it's superconducting. Now here I have a ring of magnets. I have a ring of magnets, and we're going to have to talk in more detail. Yeah, we have 3 minutes left. We'll have to talk in more detail next class about what exactly is going on here. But you know already that if I take a conducting piece of material and put it near some magnets, I'm going to get currents. So I will have currents flowing in there. And so I'll get levitation, which again is understandable from a classical perspective. When I take a piece of metal and I put it near a magnet and it repels, classical physics tells me why that's going on. I'm getting induced magnetic fields and I'm getting repulsion. What classical physics can't tell me is the other crazy part of the story, which will, I should be wearing gloves, that would help. Okay. What classical physics doesn't tell me is why I get something called flux pinning going on here. Yeah, what is right? That's completely bonkers. And so I've got this permanent magnets here, and I've got a strong magnetic field on top of this table. And that superconductor, when I placed it on there, do this with gloves. When I place it on there, it's locked in place due to the magnetic fields that are actually penetrating in certain spots through that superconductor, which classical mechanics can't tell me, first of all, why it's superconducting, but classical mechanics also can't tell me why I'm even getting some electric field to penetrate and therefore be pinned in space. And so I think you can see it. It's floating. I could probably even, let's see, it's definitely floating over there. Yeah, it's going to float right over. I could put a barrier on top of here, and it's going to float right past. So drive your car now, because eventually we're all going to be cruising around in these things. There it is. So next class, we'll get in a little more detail about superconductivity and flux pinning and quantum mechanics, but see you Wednesday.